In this problem, we are given a beam AC, which is fixed to the wall at end A and supported by a roller at P. A point load P is applied at end C, and we are asked to find out the reaction at the supports A and B, and also the deflection function V of x in terms of the given quantities P, L, E, I, and x. Part A of the problem asks for the free body diagram of the beam. There is already an applied load P at end C. Let's call the reaction from the roller By and the reactions at end A, Ay, and a reaction moment Ma. Looking at the beam right now, we can write down the equations of equilibrium for the beam. So we are going to have summation of forces in Y being Ay plus By plus P equals to a 0. Let's call that equation 1. If we sum moments, say about point P, we are going to have minus Ma plus Ay times L. Apologize, that's going to be a minus sign, plus a P times twice of L being equal to 0. Let's call that equation 2. Looking at the system of equations 1 and 2, we recognize that there are going to be three unknowns, Ay, By, and Ma. This makes the system indeterminate. It also means that we are going to need additional equations to solve the system, which is where part B of the problem comes in. In part B of the problem, we are asked for the geometric boundary conditions at supports A and B. We recognize that A is a fixed end at the ball, and therefore both slope and deflection are limited. At B, which is a roller joint, it's only the deflection that's limited, but there is no restriction on the slope. So, summing up the geometric boundary conditions, we are going to have at end A the slope being equal to 0 and the deflection also being equal to 0. At B, we are going to limit the deflection to 0, but remember there is no restriction on the slope. The next part of the problem asks for the deflection function Vx and also the reactions at the supports. We know that V double prime times Ei equals to the bending moment. If we look at the beam in general, we realize that there are going to be two intervals. The first being before the roller joint, AO, and the second being after the roller joint, as seen in free body diagram C. We would therefore need to evaluate the bending moment expression in both these intervals. Let's look at the first interval. Now, this is the interval that's from 0 to x to L. And for free body diagram C, we are going to have the interval starting at L, going all the way to the end of the beam at 3L. In free body diagram A of P, we are going to have a force Ay, a moment Ma, a shear force V of x, and an internal bending moment M of x. Similarly, for free body diagram C, we are going to have a force Ay, the roller reaction Py, the moment Ma, the internal shear force Vx, and also the internal bending moment M of x. By observation, it looks like the evaluation for internal bending moment for part C, it's going to be a lot easier if we actually consider the right hand side of the beam. So for this part, we have an applied load P, the shear force Vx, and the same bending moment Mx. We will start the analysis now to find out the deflection functions in the two intervals. For segment 1, which is this range, summing moments about point O, we are going to have the internal bending moment mx being equal to ma plus ay times x. Let's call that equation 3. We will use the definite integral approach for this solution, which means that slope function theta x is equal to the slope at the left hand side, that's equal to theta a, plus 1 over ei multiplied by the integral of m of x dx. Since this is a definite integral, we have the limits of integral being the lower limit being equal to the left hand side, which is equal to 0, and the upper limit being x. Note that the expression for bending moment we are going to use in this case is going to be the one that we derived in equation 3. And also that from the geometric boundary conditions, theta a equals to a 0. So if we plug in equation 3 and integrate the expression, we are going to end up with theta of x being equal to 1 over ei times m of a multiplied by x plus half ay x square. If we were to plug in x equal to L into this equation, let's call that equation 4 for now. So theta b, which is the slope at P, is going to be equal to theta L equals to a 1 over ei times mal plus half ay L square. Let's call that equation 5. To calculate the deflection function, we have v of x being equal to v of a plus the integral from 0 to x of theta x dx, where theta of x is the slope function in the interval 0 to x to L, which is what we have in equation 4. We also note that the deflection at end A equals to 0 since it's fixed. We also discussed this in the geometric boundary conditions. So once we plug in equation 4 and integrate the expression, we are going to end up with v of x be equal to a 1 over ei times ma x square over 2 plus 1/6 ay x cube. So if we wanted to find out what the deflection at end B is, we are going to have VB being equal to VL equals to 1 over EI times MA times L square over 2 plus 1/6 AY L cube. From the geometric boundary conditions, we know that P is fixed with respect to vertical deflections, so that ends up being a 0. Let's call this equation equation 6. Equation 6 is an equation involving MA and AY. If we scroll up to our static equilibrium equations, we also see that there is another expression involving MA and AY where these are the only variables. So if we solve equation 2, and 6, we are going to have AY being equal to 3P and MA being equal to minus PL. If we scroll back up and look at equation 1, We now know the value of ay, so we can solve for by as well. So once we substitute ay into equation 1, we are going to end up with by being equal to a minus 4p. Once we substitute the value of the unknowns into the equation for Vx, we are going to have Vx equals to Px squared divided by 2ei times x minus L. Now this is valid only between 0 less than x less than equal to L. We are left to find out what the deflection Vx is for the other segment. So L less than x less than 3L, we are going to want to find out what the moment equation is. If we scroll up to the free body diagram for segment 2 that we have in here, let's go ahead and replicate that down below. So we have the right hand side of the beam OC, where we have a load P that's applied, the shear force V of x, and the internal bending moment M of x. Now remember that this length is 3L minus x. So if we sum moments about O, we have mx equals to P times 3L minus x. Using a similar approach, we are going to have theta of x being equal to the lower limit, that is equal to theta b, plus 1 over ei, the integral going from L, because that's the lower limit, up till x of m of x dx, which becomes equal to theta b plus 1 over ei, the integral going from L to x, p times 3L minus x dx. We know what theta b is going to be in terms of everything that's known to us, because we have solved for the unknowns. So using a similar approach again, we have Vx. Let's call that equation 7 for now. So Vx is going to be equal to Vb plus the integral going from L to x of theta of x dx, where theta of x is the expression we have derived in equation 7. So once we solve for the integral in terms of everything that's known to us, we are going to end up with Vx being equal to 1 over ei minus p over 6 x cube minus L cube plus 3 over 2 times PL x square minus L square minus 2PL square x minus L. This being valid in the range 3L less than equal to x less than equal to 3L. Now combine these two equations should give us the value for the deflection functions in both the ranges. We are left to make a plot of the deflection functions. So what we are going to do is we need to find out the deflection on the right hand side. So if we plug in 3L into the equation on the top, we are going to have V of 3L being equal to Vc equals to 11PL cube divided by 3 EI. To make a plot, let's assume the deflection is on the y-axis and length is on the x-axis. We're going to have points A, B, and C. We know that slope and deflection are both 0 at A. At B, we have a deflection of 0 but no restriction on slope. And at C, we worked out what the deflection was going to be. So if we were to assume that the deflection starts as 0, with the slope 0, it would go to B and end up at 11 PL cube over 3 EI. This concludes the solution for homework problem 7.3.